Linear momentum. Linear momentum. Linear momentum or translational momentum, or P, is equal to the mass of an object in kilograms multiplied by the velocity of that object in meters per second. So the SI unit of momentum is a kilogram times a meter per second. Now, basically, the more momentum an object has, the harder it is to stop it. And there are two components, obviously, to momentum: an object's mass and its velocity. If an object has a relatively small mass, like a bullet, but a relatively high velocity, like a bullet may have as it's shot out of a gun, then it could have a lot of momentum. It would be difficult to stop. Or you could have something like very massive, like a freight train, which may be only going a measly 5 miles per hour, but again, that has a lot of momentum. I would not want to stand in front of the freight train. It would roll right over me. Now, how does Newton's second law apply to momentum? So, F equals ma, or the sum of the forces, is equal to ma. And that is equal to the mass multiplied by the change in velocity over change in time. Now that's equal to basically a change in momentum over a change in time. We could also write this as the net force multiplied by a change in time is equal to the change in momentum. Now, this net force multiplied by a change in time has a special word. It is called impulse. And we are talking about impulse if we're talking about the time of impact for a collision. So we have a certain time for collision, and we know the force during that collision. That is equal to the change in momentum of that collision. Now, if your change in momentum of that collision is constant, then we can look at the relationship between the force applied during the collision and the time during the collision. And one of the things we've noticed is if we can increase the time during impact by cushioning, for example, we will then lower the force of impact. And this is the idea of, for example, airbags. If you have a collision in a car, the airbag comes out. It's supposed to increase your time of impact and therefore lower the force that you feel during the collision. So how can we solve for impulse when we're looking at a graph? If we had a graph of force versus the time of impact, and we showed on the graph here that we have a varying force, so the force is not constant, we could find the total impulse of a particular collision by just determining the area of the function. We can also find the total impulse by simply finding the average force value of the graph and multiply that by the total change in time, which would fall right there to right there. And if we could find that area by multiplying the average force by the total change in time, that would also give us the total impulse. Okay, so let's do an impulse example. Let's say we have a tennis player ready to serve a ball. When they first serve the ball, it has an initial speed of 0 meters per second. After they hit the ball with the racket, it has a speed of 55 meters per second. The mass of the ball is 0.06 kilograms, and the time of impact is going to be 4 milliseconds, or 4 times 10 to the minus 3 seconds. Now this is our given for the problem, and what I want you to find is what is the net force on this ball during the collision. I know we have a formula for impulse, which is your net force multiplied by the change in time of collision is equal to the change in momentum, or the mass of the object, multiplied by the final velocity minus the initial velocity. So the formula I'm going to use for force then is my net force is going to be equal to the mass of the ball multiplied by its change in velocity all over the time of impact of the serve. Okay, so plugging in the numbers, we get a net force of approximately 800 newtons. Alrighty, so now we're going to talk about conservation of momentum. And conservation of momentum is basically your total momentum before a collision is equal to your total momentum after a collision. Typically this is for two objects, so you'd have the momentum of the first object before a collision plus the momentum of a second object after the collision is equal to the momentum of, whoops, I made a little mistake there. This is the momentum of the first object before plus the momentum of the second object. Alright, one more time. Let's try this again. So it's the momentum of the first object before plus the momentum of the second object before is equal to the momentum of the first object after the collision plus the momentum of the second object after the collision. Now writing out the formula for momentum, that's the mass of the first object before multiplied by the velocity of the first object before plus the mass of the second object before multiplied by the velocity of the second object before. That's equal to the mass of the first object multiplied by the velocity of the first object after the collision plus the mass of the second object multiplied by the velocity of the second after the collision. Alright, let's do an example with this. So I have two railroad cars. We'll call this one railroad car 1 and this railroad car 2. And railroad car 1 is moving towards railroad car 2, which is at rest. And this is before they collide. After they collide, both railroad cars stick together and move along to the right. Now the mass of each railroad car 1 and 2, are equal, and they each have a mass of 10,000 kilograms. And the velocity of railroad car 1 before the collision is 24.0 meters per second. The velocity of the second railroad car before collision is 0 meters per second. And the question is, what is the velocity of the railroad cars when they're stuck together after the collision? To solve for the velocity after, we're going to use the law of conservation of momentum and say the mass of the first object multiplied by the velocity of the first object before plus the mass of the second multiplied by the velocity of the second before is equal to the mass of the first times the velocity of the first after plus the mass of the second multiplied the velocity of the second after. As I've already mentioned to you, the masses are all the same, so we're going to get rid of the subscript for the masses. And then hopefully also you can see that if the masses are all the same, we can cancel out all the masses. Also, the velocity of the second object before the collision is 0 because it was at rest. So when we look at this equation, we have the velocity of the first object the first object before is equal to the velocity of the first object after plus the velocity of the second object after. Now, the two railroad cars are stuck together after the collision, so their velocities after the collision are the same. So I'm going to get rid of the subscripts here, and then rewrite this as V1b is equal to 2v sub a. And therefore, v sub a, we just divide both sides by 2, and I will get a value for v sub a of half of v sub 1b, or 12.0 meters per second. All Alrighty, let's do another example. So what I have here is a rocket before launch, R for rocket, and after it starts to launch, we have our rocket, but we also have gas that comes out of the rocket. So there's going to be a momentum of the rocket to the right, and based on my picture, there is going to be a momentum of the gas to the left after it starts to launch. Now, our given is we have a mass of the rocket is 5,000 kilograms. Let's say the total mass of the gas is 120 kilograms. And the velocity of the rocket to the right after it launches is 1,200 meters per second. So, what is the velocity of the gas as it launches? Alrighty, the formula we're going to use for this using conservation of momentum is the mass of the rocket multiplied by the velocity of the rocket before launch plus the mass of the gas multiplied by the velocity of the gas, which is inside the rocket before launch, is equal to the mass of the rocket multiplied by the velocity of the rocket as we launch plus the mass of the gas multiplied by the velocity of the gas as we launch. Now, before launch, we notice that the rocket and the gas are at rest. So the velocity of the rocket before and the velocity of the gas before, those are zero, and these terms just cancel out. And then what I would like to do is subtract the mass of the gas multiplied by the velocity of the gas after on both sides. I'm trying to find the velocity of the gas after, so I'm going to divide both sides by negative mass of the gas. And so I have an expression for the velocity of the gas after. Let's go ahead and solve. So the velocity of the gas after is negative 50,000 meters per second. That negative is very important because it is indicating a direction of left. Keep in mind that velocity is a vector, so not only do we have a magnitude, but our answer will also give us a direction. And that is also the case for momentum. Momentum is also a vector, so if we have a negative value for momentum, that means that the object has a momentum in a negative direction. Okay, let's talk about collisions. So when we're talking about conservation of momentum, there are two types of collisions that are very important to discuss. The first type is called inelastic collision or inelastic collisions. And in inelastic collisions, energy is lost to the surrounding environment during the collision. Now, this is typically in the form of sound or heat or light, or perhaps during a collision some items are damaged during the collision. If you hear or see or feel or there's damage in a collision, you know energy has been lost during that collision. Now, even though some energy can be lost during a collision, the momentum is not. The momentum is still conserved. As a matter of fact, in any type of collision, the momentum is always conserved. Now, there is a special case of an inelastic collision, and this is called completely inelastic collision. And this is when two objects collide, and during the collision they stick together and then they move along together after the collision. And of course that, as I said, has a special name, completely inelastic. Alrighty, now I would like to talk with you about a special example of a completely inelastic collision. This is the traditional physics example of the ballistic pendulum. Now, with the ballistics pendulum, you have some sort of mass hanging from a fixed position, and you have a projectile, such as a bullet, heading towards the hanging mass. The bullet then, when it collides with the hanging mass, becomes embedded within the hanging mass, and the hanging mass and the bullet move together, swing upward towards the top of a swing together. As the bullet and the mass system are together, the total mass then will be the m1 plus m2. This is an after situation, so right when the bullet and the block move, right after the collision, they move together, and there is this speed afterwards, what I call a VA. They each have the same VA, or velocity after, because they are stuck together. There is a height difference between the bottom of the swing and the top of the swing, and I'll write that blue H here. And the goal for this example is to find an expression between V1b and the height that I've written in blue, the maximum height that the bullet and the hanging block reach at the top of the swing. Using conservation of momentum, we have the total momentum before the collision is equal to the total momentum after. As I said earlier in the problem, the wooden block before it is hit by the bullet is at rest, so we can get rid of that term. And I can also get rid of the subscript of V1 and VA because the masses are moving together. It's a completely inelastic collision. Solving for V1b, then, I'm going to factor out the VA on the right side of the equation, so I'm left with V sub A multiplied by the quantity of m1 plus m2, all divided by m sub 1. So now I have an expression for V1b. That's great. But on the right side of the equation, I don't have H in there. So now what I'm going to do is look at conservation of mechanical energy from the last chapter to find a new expression for VA. Conservation of mechanical energy says the total mechanical energy at the bottom of the bullet block system is equal to the total mechanical energy at the top of the bullet mass system of its swing. And so we're going to apply this idea by taking the total kinetic energy at the bottom plus the total potential energies at the bottom. We're going to set that equal to the total kinetic energies at the top plus the total potential energies at the top. At the bottom of the swing, there is only kinetic energy because we're going to make that our reference level. There's no elasticity as well, so the potential energy at the bottom is gone. At the top of the swing, the only type of energy there is gravitational potential energy, so our kinetic energy value is gone. So writing out these formulas, the kinetic energy at the bottom of the swing after impact is the 1/2 multiplied by the combined masses multiplied by the velocity after impact squared. And that's equal to the gravitational potential energy of both objects at the top of the swing. Hopefully you can see here that the masses do cancel, and then by rearranging this formula for V sub A, we get the square root of 2gh. And what we're going to do is take the square root of 2gh and plug this in for VA up above, right here. And when we do that, our new expression looks like, isn't that beautiful? Okay, there is another type of collision, and this is called an elastic collision. With the elastic collisions, or with all collisions, momentum is conserved. But also, number 2 here, the energy is also conserved, and in this case we call it kinetic energy. So we have a new formula to add in our mix of formulas. So when we have an elastic collision, we can also use the formula that the velocity of the first object before minus the velocity of the second object before is equal to the velocity of the second object after minus the velocity of the first object after the collision. Typically, when we talk about elastic collisions, this is in regards to billiard balls, or if you play pool, any type of balls like that. So I want to give you just a real quick example. Okay, we have billiard ball 1 moving towards billiard ball 2 at rest before a collision. After the collision, what happens to their velocities? We also know that they all have the same mass. Using conservation of momentum, we come up with this formula. We know that the masses are all the same, so we can get rid of the masses of each one. We can cancel them out. We also know that the velocity of the second ball before the collision is 0, so we can get rid of that term as well. So now we have this expression for the velocity of the first ball before the collision. Using conservation of kinetic energy, because we're going to assume this is an elastic collision, we have another formula we can use. We already know that the velocity of the second ball before the collision is 0, so we can get rid of that term. And so I have another expression for v1b. I would like to then take this expression and set it equal to the one above. So I will have this is equal to v2a minus v1a. Just rewriting this and then combining our terms, I see I will have v1a plus v1a is equal to 0, or 2 times v1a is equal to 0. In other words, the velocity of the first object after the collision is 0, and all of the energy is transferred over to the second object, so the second object has taken on the speed of the first object. Okay, here's your practice, and good luck.